Here's where. Sorry. Let me see if I can talk. Good morning, everyone. Sorry, I hope you guys can hear me. Thank you, Vicky. Yeah, today yesterday was Thanksgiving, right? 感恩节，对，现在在 US 现在 right now 是感恩节，然后 tomorrow 是 Black Friday， 对 ，yeah.
Only parents with small kids notice
the little holidays, right? Yeah. So I'm really grateful everyone is here in the early morning and close to Thanksgiving. Anyway, so last time where we end, I think, is something called Lyapunov function method. Basically, the idea is, suppose here is whatever the differential equation system we have. It's an autonomous n-dimensional differential equation. You guys can hear me, right? And last time we assume origin is a fixed point. It doesn't have to be. Now I just put it in more general way. And so I combine the two results we discussed before into one. So X bar is whatever the fixed point you care about. Now you want to know the stability. Could be local, could be global. And now if I have a function, this is a scalar function, defined on what? On an open neighborhood. Did I say open? So defined on some open neighborhood of U, which contains 0. And for this function, first of all, this function is going to be non-negative. This 0 is really a mathematical simplification, okay? But where is going to be 0? This function is only going to be 0 at your fixed point. All the other place will be above 0. Again, 0 is your minimal level. This is just a mathematical simplification. You got the idea. Think about if you have some sort of generalized energy. So at the fixed point, you have the lowest energy. Any other place, they have higher energy. So that's the first one talk about. And the second one, and the derivative basically is along the solution flow of the system, dv dt, is, as you can see, if you use chain rule, that's basically gradient v dot f, or dx dt. Partial v, partial x, and with what? Dx dt. Anyhow, so when that one is less or equal to 0, we know when you're approaching some stable equilibrium, actually, your energy is going to be decayed, right? Because you're stabilizing, trying to stabilize yourself close to the equilibrium. So dv dt is going to be less or equal to 0 as time goes, and you're not going to be increasing. And last time, I think we talked about this. Of course, this is true, but now we don't have to check what happened to X bar. So now, to be more consistent, I'm adding this back. What I'm saying is the last time, what I said is the x dv dt is less or equal to 0 on the entire U. We don't have to. And meaning we don't have to consider what happened to X bar. We can take out the X bar. You can do more, meaning on the entire U, check everything. Also, you can take out that point, check on the neighborhood. So then in this case, the equilibrium, whatever your X bar, is going to be diagonal stable on you, on this neighborhood. But if you can replace 2 by 3, 3 is stronger. And so the strict inequality holds on the same place. Now you're going to see asymptotic stability. Asymptotic is compared to diagonal stable, and asymptotic is saying we're going to asymptotic getting closer to X bar. So you're going to see, and the Lyapunov function actually on some sort of energy is going to strictly decrease. You cannot stop until you reach that. So that's where we were last time. Now, sorry, I forgot to check online. If anyone online, could you guys see us and hear us okay?
Yes, thank you very much.
Thank you. We talked about this, but I never show you what exactly this is. We used this before. Something called LaSalle invariance principle. 我相信那个老师们应该都见过，对吧？对，都见过。要 talk about this, we need to introduce some notation, something called limit set. So this basically you select all the point in your domain, whatever your domain, suppose it's Rn, your domain. Now you're collecting the asymptotic behaviors. So this is our notation. You start with this point. Let's use X. So X naught. Now your convergence to this R is all good. Let's do star. Sn goes to D. So basically what this is saying we're trying to collect the asymptotic pushing time back forward. Asymptotic behavior when you start with single point x0, where you eventually go. So that's something called omega limit set. This is the omega limit set. This is called the omega limit set. For systems start with
XT then.
yeah, thank you. So let's say K defined to be the largest invariant set. That is true. So suppose now it's defined R doesn't have and it will be the T X. And last time we used V dot equal to 0. It's basically your Lyapunov function settled. It's where your Lyapunov function settled. Here's the set. Now we are trying to collect the largest invariant set in the set. Let's say that's called K. So here is that's how this invariance principle. If we know the solution, again, this means the system, we start with x0 and here's the solution T. All the other times, sometimes you see we use solution flow and this notation, they're the same. So now if we know the solution of the system star stays entirely in the domain, we don't have the degree. Right now it's Rn. What I'm saying is the system you consider doesn't have to be doesn't have to be defined in the entire Rn. So for instance, if we assume this is true, and D is a subset in Rn, meaning whatever the domain you're working with. Now we know initially, once you consider solution, you cannot get out this region. This is what this is saying. For t bigger than 0, all the positive orbit basically stay in D. Then we know the omega limit set intersect with whatever the domain you care about. So here we have to do the similar thing as well, because the general domain doesn't have to be the entire thing containing K. And in particular, what's this is saying? This is saying the asymptotic behavior in whatever the domain you care about actually must contain in the largest invariant set. And in particular, here's the corollary. Suppose if further, this one consists of a single point. What should I be? Let's say P single point, let's say X bar. Then this point must be an equilibrium solution. And not only that, here's the thing we usually use. All the solutions indeed actually will converge to X bar as t goes to infinity. So this is saying, and this is the case we use a lot. Suppose the largest invariant set we just defined and is composed of only one point, 就是这里就一点。这个时候呢 so in this case, now we know if this is true, where you go, no matter where you start, you will stay. This is saying all the solution eventually will converge, start in D, and will converge to that point. But that doesn't mean this point, a fixed point is okay. Doesn't mean this point is what? Asymptotically stable or globally asymptotically stable in D. But if you know this fixed point is locally attractor, then it must be the case. So that's the thing we use a lot. What I'm saying, this is not sufficient to tell X bar is globally asymptotic stable in D. And you have to know if locally you're getting close to something doesn't mean this is what? This is GAS. All right. So now second thing, I think we're done with the stability for equilibrium. We did local analysis, use spectral analysis. Basically, you did linearization, look into the spectrum, that's local. And global, one thing we can do is Epsilon function method, and you can verify the global stability. And this one, a lot of time this is saying that the dynamic is pretty simple. You see all the solution long time and they're approaching that. So this point must be GAS, globally asymptotic stable. That's all. Now we're going to move to next chapter. So you know there are two interesting objects. One is equilibrium solution, and the other one actually is periodic solution. So now we're going to move to that and to talk about it. So for this, we will see something called flow rate theory. So let's say here x equal to p of t. This is our periodic solution. We are non-constant periodic solution. So for sure, you will see PS a lot. So this is not like the PS with complete, it's a periodic solution for sure. Of period, say capital T of the system stuff. And let's say gamma this is the orbit. And here comes the question. Remember how we define stability of fixed point. 我们怎么想那个单点的稳定？我们想的是说，当我们 initially pretty close， 我们会 stay close， 叫 start close, remain close， 对吧？我们是这样定义的。可是 for periodic solution, can we do the similar thing? We were wondering, right? So let's see an example. So for this one, indeed, there are a lot of my detail. We'll just draw one of the part. So we see there are lots of mini cycle here in between. Sorry, it's not perfect. Yeah. And a lot of mini cycles. So what I'm drawing here, the x-axis is x, the y-axis is x prime, the dx/dt, the phase space. And this one, actually, we can use what? First integral method, find the solution by doing energy method, right? Multiply x prime on both sides, so we can find that. Anyhow, that's not the point. The point is, look, so I have a lot of limit cycle. We already know, and we're going to know. And those limit cycle, not limit cycle, periodic solution, they're stable. But suppose initially here I have one. Here is another one I call P0, Q0. Here is how far they are, pretty close. But once, because they have what? They have, even they're periodic, they have different periods. And so say one is faster than the other one is slower. And by time t, you're here. By time t, the other one's here, you see? And you start close, not necessarily you'll stay close. It's just like what? So you have two runners on the road. They're pretty close in the beginning. But one guy is a marathoner, so it can run so fast, right? And maybe after a certain time, and they come back to see each other again, but one guy actually is already at least one round like further ahead of the other guy. You see what I'm saying? Because of different period. So we can now say start close, stay close. So how we're going to characterize something called stability for limit cycle? Any suggestions? You got what I'm saying, right? 我说如果是点的话，它是局部稳定是 start close, stay close. 否则它就 repeller 嘛，对吧？它是一个 local attractor, start close, stay close. 但是如果你有一个 periodic solution, you cannot do this anymore. The concept of stability of periodic solution is way more involved. So any suggestion how we're going to capture those? How I'm going to say, here I have a periodic solution. This guy actually is stable or attractive, at least locally. How we're going to characterize that? Any suggestions? 这个时候我们就不能只看一个单点的运动，我们要看什么？我们要看什么？我们要看，假如说这是你的一个 periodic solution, you are pretty close, and you want to know what? As time, intuitively, as time getting further, you are not far away from the entire orbit. So this case, we cannot do point and we cannot try the similar thing as we did for the single point or equilibrium solution. So let's do this together. So basically, this case, periodic solution. Is said to be arbitrarily stable. If what? If for any epsilon bigger than 0, there exists a delta constant such that what? Such that initially, say you're at P0, you're close to, I should say, initially called X0, you're pretty close to the orbit initial time. And this one implies what? You're going to stay close. How are we going to describe stay close along the entire orbit? What are we going to do? So that's the fundamental difference. What we're saying is they are all stable periodic solution, but they have different period. So one guy is running faster compared to the other one. How are you going to track how close they are? We can use set distance, right? We compare at any time. This is a solution we start with. And at time t, here's where we are. Then compared to entire gamma, that's what we define, this orbit. This distance is less than epsilon. Does that make any sense? Do we know how to define the distance between a point and the set? Is the infimum, right? If reachable would be the minimum distance between this point and any point along your set. So that's called the distance. So far, so good. So this look into the infimum. What's this? This is the infimum of all the y. Y is on gamma. Right? We know how to measure the distance between point and object. We look into the smallest, closest spot. So this is the difference. We cannot do what we did for a single point anymore. So this is called arbitrarily stable. Of course, we can define something called asymptotically arbitrarily stable.这个怎么写 X confuse？ 这个 X 和这个 X 不一样哎。我说 X， 就叫 PP 好了 ，periodic solution PP。is arbitrarily asymptotic. Of course, first of all, you have to be arbitrarily stable. So the gamma orbit First of all, P of T is similar to what we did for asymptotic stable for fixed point. Then, what's more? If you can find a neighborhood such that if initially you are in the neighborhood of our neighborhood of P0, then what happens? Then the distance is going to be getting closer. So that's what the asymptotic means. You see, idea-wise is similar as what we did for asymptotic stability for fixed point. The punchline is, here is a difference. We're going to measuring how far you are away from your object, your periodic solution, not a point anymore. Not time, not by time. Okay, all right. Then we're going to know how to analyze. We want to know how to analyze, how to study the stability of periodic solution. And so now we're going to linearize the system star and evaluate at periodic solution. So what do we got? We're going to see this linear system. Right? This one. So now, this guy. So let's call this question 3. So then, closed theory. So first, the fundamental solution of the linearized system we call 3 can be written as in the following way. So we can see how the fundamental structure-wise, how it look like. So let's say YT is equal to QT and ELT. What's Q? This is n by n function, n by n matrix function. Period. It's a periodic. In terms of T, it's periodic, but fixed T is an n by n matrix. And QT also at 0 is identity matrix. This is n by n identity matrix. And L is a n by n constant matrix. The cool thing about this, once we know the structure, and we will see the eigenvalue of L, all the eigenvalue of EL evaluated at period will tell us things of stability, tell us the stability of the periodic solution. Let's see how. And for that, we need to introduce some notation. I'll put the notation here. So the eigenvalue of L we call them as flow with exponent. And the eigenvalue of ELT, this basically is what? It's a Y capital T. It's a fundamental solution. You evaluate at capital T. When you evaluate capital T, you get Q capital T, EL capital T. But what you know Q, what do you know about Q? This is a matrix function with period what? T. So Q capital T equal to Q0. What's Q0? Identity. So when you evaluate one period, that's exactly ELT. So far, so good? So this is known as the flow-quick multiplier. And then here's the result. The linearized system we call 3 has a, of course, non-constant periodic solution. Has a periodic solution. And a period T, capital T. If and only if the flow quick multiplier, one of the flow quick multiplier is 1, or one of the flow quick exponent is 0. So we know this is necessary and sufficient condition. So you can use this to identify the periodic solution by looking into this kind of structure. However, one thing I have to, there are a couple of remarks. One thing I have to warn you is, in general, it's very hard to calculate this. So for people familiar with this flow quick theory, and you know this one has another name. This is known as monodromy matrix. Because this matrix tells us a lot, many information and about the periodic solution. This you can think about sort of, not quite right, and related to what? The Jacobian matrix at fixed point. So the eigenvalue, the real part eigenvalue telling us the stability. Now, and this one, monodromy matrix or ELT. And the spectra of that one and telling us the stability actually is a periodic solution. So this is, and actually you can see pretty easily why one, if you have periodic solution, and one must be one of the eigenvalue. Do you guys want to see that? Oh, we can skip it. I'm saying you can see one is the eigenvalue. Because what? The idea is you start on periodic solution anywhere, say P at 0, look at the tangent. And now after one round, you see the linear system send the tangent to, tangent means P dot 0 to B dot T. What I'm saying is, here is the periodic solution, and here is the tangent. Now, after one period, where you come back? You come back to this, but you become P dot T. But this is periodic, they're actually identical. So, see, look at this. we know this is the solution. Is that right? It's a solution. Periodic solution, special, doesn't matter if you're pure or not. If you're a solution, meaning you satisfy your equation, right? So now if we differentiate this again, I'm going to write the one derivative by dot. So now what do you got? You got f pt dp dt is another p dot, right? So this exactly is what satisfy the linearized system. dy dt equal to, oh, I didn't put this right, the Jacobi. This is a chain rule. This is a chain rule, right? Jacobi. So this is exactly the linearized system 3. Satisfy that. So now you can, oh, sorry, what? Yeah. So now you can see if, look at this. I know I give any initial condition, let's call V0. Where are you going to go? You're going to see this one, send V0, we call V of t. This one is a linear system. But now if you take V0 to B, the tangent at your initial location, okay? So where you send? You send that to P dot of t, right? Because it's set in the linear system, after one period, you're back to capital T, right? However, we know this is a periodic solution. So what's the relationship between those? You come back. So those are identical, right? This is a periodic solution. Pt plus capital T equal to Pt for any t. When you evaluate t at 0, that's exactly what you see, right? And you differentiate and evaluate t equals 0. That's exactly what you see. That's it. So look at this. So I'm going to rewrite this as p dot 0 sent to p dot t. But this one is same as this because periodic condition. So we know it's p dot 0 equal to yt. This is a monodromy matrix, p dot 0. What's that means? You find the eigenvector. What's the eigenvalue? What's the associated eigenvalue? That's it. Anyway, back to this. So, and the other comment I would like to state, since you know the monodromy matrix, the eigenvalue, one of them must be 1. So we can, I'm going to clean this part. Let me clean this one. Is this okay if I clean this part? Are you done? So in other words, here's the second remark. So from here, it's a monodromy matrix. Second remark is the quantile of the periodic solution, T, okay? 是什么呢? Must be 1. Let's call the rest is lambda 1. First one lambda 0, lambda n minus 1. Must be like that. Then here's the next result as a follow-up of the flow theory. So now we say the periodic solution, this one is arbitrarily asymptotically stable if what? Your boundary is 1, not like the fixed point case. Your boundary is is 0. Now your boundary is 1. You want to control, make sure all the spectral radius is less than 1. Because this is essentially related to something called Poincare map. We probably were not going to discuss it here. But so for the mapping, and this is, yeah, that's too much. Poincare map, you start and go to something called transversal plane. You come back, you want to see whether or not this map has a fixed point. If it has a fixed point, it's going to be your periodic solution. Anyway, so and if all the lambda I is less than 1 for I, you are within the unit ball for the spectral radius. You're not going to escape that. But one of them, at least one of them, must be on the boundary. And for 2D case, we can even do better. So n equal to 2, two-dimensional system. This is Poincare stability condition. Now, a T-periodic solution. Of a 2D system. This is only for 2D. Because of what? Because of this. Is habitually asymptotic stable if the integral from one period, the divergence of FET T is less than 0. The key reason is coming from something known as Lewis theorem. So the key, how to see this. So you know, because why this is 2D? In two-dimensional case, how many eigenvalues you can have, or how many flow-coed multiplier you can ever have in 2D? First of all, the periodic solution, unless you're in the polar coordinate, this must be at least 2D periodic solution. And second thing, that's the minimal dimension. But second thing I'm trying to say is, if you have an n-dimensional system, you're going to have totally n flow-coed multiplier, and one of them we already know by the theorem is 1. So now my question, if you have two-dimensional system, how many flow-coed multipliers you're going to expect? This is an n-dimensional case. How many flow-coed multiplier we have? N, right? So one of them must be 1. If this is 2D, how many we're going to have? 2, exactly. And also the point line is we know one of them. So now, you know, this one, say lambda, we call lambda 0, lambda 1. Lambda 0 is 1, right? By the theorem. This is what? The determinant of what? The determinant of why the monodromy matrix. We talk about this in the trace determinant plane, right? The product of the eigenvalue equal to the determinant of your matrix. And then by Lewis theorem, we know what? This equal to exponential, this integral, the trace of the Jacobi evaluate pt dt, but which indeed is what? The divergence. You see, the nice thing about this result is what? The nice thing about this result is, in general, if you have 3 or more, and structure-wise, you still have that. But the sum of this cannot control how big each of them it is. But when you're in 2D, you have only one unknown what? Flow rate multiplier. What I'm saying is even the products less than one doesn't mean each of the factor is less than one. But for 2D, we have only one unknown flow rate multiplier, so we can determine everything. And now, by the theorem, you know you want what? This magnitude to be less than one. This magnitude to be less than one. Clearly, this exponential function, this function must be positive, right? Cannot be negative, cannot be complex or anything, must be positive. That's first thing. Second thing, if the divergence is negative, what happened to exponential negative thing? Exponential to something negative must be less than one. So that's the key idea. So you know the stability. Indeed, and you can capture if a T-periodic solution is unstable, 2D only, okay? Because in general, even you know what happened to a product, it doesn't mean you know what happened to each individual multiply lambda k. Anyway, when this divergence is bigger than zero, exponential something bigger than zero is bigger than one, so that case you must have an unstable limit cycle. Sorry, periodic solution. You guys with me? Because you know how big lambda 2 is. In 2D, the other case when the divergence is positive, exponential positive thing is bigger than one, so lambda 2 must be bigger than one. So it must be unstable. And when lambda, when you are at the boundary, and this is similar to the when you look at the Jacobi of the fixed point has zero eigenvalue. That's the inconclusive case, the tricky case. So for periodic solution, and the key is to look at the size of the flow rate multiplier. If the magnitude is all less into all, meaning the flow rate multiplier all less into a unit ball, you are expecting you have inside the unit ball except one, at least one, so you expect stability. Otherwise, if outside one, you expect unstable periodic solution. But if you are on the boundary, you have to study further. So that will be the degenerate case. Similar to, say, in the single point, fixed point case, the eigenvalue, if you have what? Everything real part less than zero stable, but at least one of the real part is positive, you're out, right? So unstable. But when real part eigenvalue is equal to zero, that's something called non-hyperbolic fixed point. You have to study further because it's a degenerate case, similar. But now the boundary is one. Okay, is this fine for everyone? All right. So where we are. So now we all know how to study the global dynamic for 1D, right? Because 1D case, you have scalar case, you can do what? You draw the baseline and you can see everything clearly. So I'm going to skip that part. Is that okay? Because in 1D's case, it depends on the slope. That's basically the slope of the vector field at the fixed point. If it's a positive, you have an unstable fixed point. If it's negative, you have a stable fixed point. So that's super clear, the dynamic. So now what we're going to do, we're going to go to the global dynamic of 2D. And here, what I owe you, we already used boundary result from here, but we never say clearly what's this theorem, what's that theorem. So we're going to make it up right here. So we just defined the omega limit set. And here is that's asymptotic behavior. What's the property of omega limit set can have? And first, this must be closed.这个是为什么呢？是因为它怎么看这个 omega limit set? How we're going to see the omega limit set? 这个是我还没定义哈，我得先定哦，后面这页写。What's this? This is the forward orbit when you start at this point. Do not be confused. I'm talking about I start at Y when T is positive. This is the forward orbit. Now I take the closure. This must be a closed set, right? This is saying going forward, I'm trying to capture where I'm going. Start anytime. Let's say time right now is 0. Now I have 1. But when time is 1, I take discrete time series, your favorite, right? T equal to 1. Now I go further. What's the difference? And here is time at 0. Here is gamma plus. When you start at, unless this is Y, and x0, Y. But now when T equal to 1, you start at this. And T equal to 2, you start at this. So it's what? When T is getting bigger, your forward trajectory is getting shorter, right? Then the intersection is capturing where you're heading for. So that's the omega limit set. But the point is super easy. We all know it's a topological property. And if you have a closed set, the arbitrary intersection of closed set will be closed. It's just like the arbitrary union of open set will remain to be open. So this is a closed set. And second thing, this is important. If the forward orbit start at x0 is bounded, it's under control. Now we know more. Now we know the omega limit set is non-empty and compact and invariant. Invariant is always true. Is non-empty, compact, and connected. Meaning asymptotic eventually must be go somewhere. Do you know why? Because if you take this one and its equivalent, you take, say, a sequence that's go to infinity. They're the same. I'm saying you take arbitrary T positive to look at the intersection of the closure. It's same as you take a positive sequence Tn goes to infinity. And then this one will be a nested set. Nested is getting smaller, and which is shrinking. Intersection net compact nested set actually is what? It's non-empty. So that's where it's coming from. But the good news is saying when you start somewhere, everything is in the boundary region. Now you know where you're heading for. You must be heading somewhere. I don't know where, but somewhere. And that set also must be compact. And connected means you start anywhere, you can go the other place. Suppose it's a limit cycle, you can start one point to get to the other point. And some other cases could be simply a fixed point. And it must be invariant. So that's all the nice property about omega limit set. And similar thing happened to when you move time backward. That's called alpha limit set. just you tune, you change your clock direction, you go time, you time traveling back. Indeed, I think we just don't have enough time to study periodic solution. One fundamental, I think, the key tool is something called Poincare map. I highly recommend if you're a graduate student, if you're a student interested in that topic, just grab any textbook and look into Poincare map section. Here we just get a little bit of flavor of this. So, for omega limit set, you can imagine you can have what? Just like that, right? This is example of omega limit set, this omega limit set at this point. Or you can have this omega limit set. And this is the tricky, for this one I have to talk more. The omega limit set is Q. But what's P? P is the alpha limit set. Alpha and omega, the simple difference is time direction. Here's what I owe you, I promise, but never talk about Poincare Bendixson. I think I'm going to go first with a simple version. This is a useful thing. I'll call it a simplified version or simple version. What's this? Let's say I have a positive invariant. Oh. Do we all know what to mean by a set is positive invariant?一个简单的写法是说，对任何一个 x0 in M， 你 run the solution at any time t it remain to be in M， 这就叫for any t it is positive， 这叫 positive invariant。如果更好的一个 notion 是 my theory， 这叫 solution flow。You map M into M, they're the same. You stay there, so positive invariant. Anyhow. So positive invariant compact region in 2D. For 2D system. T equals X. Then我还没写出来反呢。我写出来了 ，sorry， 我把全定理写出来了。好吧，我先送你们整个的定理，不是simplified version。So for any point in the compact invariant set, okay, and one of the following must be whole. Statement. Star ADP, 他 talk about what? 就是说 two-dimensional case, asymptotically, eventually. 你刚刚说了那么多性质嘛？什么 connected, non-empty, compact, connected, closed, invariant. 这个都是你 start one point and the property. And this one telling you eventually how it look like. Here is how it look like. Star at P, the omega limit set could be a fixed point. an equilibrium solution. That's not surprising. And this also could be a periodic solution. Or this is going to be consist of finite number of points and orbits. For each of the orbit, let's call gamma j from 1 to -1. So what's gamma j? It's like this. Let me just draw those so you'll see. It's a P1, P2, P3, P4, and etc. So this will be gamma 1, this will be gamma 2, this will be gamma 3. So here, each gamma I or gamma j has omega limit set is pj plus 1, and alpha limit set is pj. But you don't have to get into that much detail. All this is saying eventually I have a clear picture for the asymptotic behavior of the omega limit set in 2D. It could be either equilibrium solution, a periodic solution. If not that, will be a finite this is called finite heteroclinic orbits. So it's very close. That's it. And the simple version, I think is pretty useful, is this. Oh, simple version. Oh. I think so. Let's say I have an open set in 2D domain. Of course, your function has to be defined, well defined on this domain. And suppose the forward orbit start with that's humor. Completed content in the compact subset indeed. And this is the omega limit set start with x0 is not a point. Does not contain any fixed point. And now you guys can guess what has to be the case. No fixed point. Cannot be the first case, cannot be the last case. Right? Cannot be first case, cannot be last case. Then the conclusion is saying, then this one must be a periodic solution. So a lot of cases, this is useful result help us to construct and find, identify periodic solutions. So suppose here is your region K, and your orbit is all completely contained in this shaded region. This orbit. Now, the key is what? If this region is a bounded trapping region, which contains no fixed point, where you eventually go? You have to end up the trapping region, top, outside pushing you in, inside pushing you out. Where you go? Limit cycle. So this is the very handy result and can help us to determine the periodic solution. And the other way, sometimes you don't even need this whole. You just do what? This. You say you have a fixed point, just one, okay? But this point, fixed point is what? It is a repeller. So it's behave, you know inside something is pushing you out. But then if this is a positive invariant region, outside is pushing you in. So where you go, eventually you have to go to some periodic solution. That's all. So now we're going to, I hope today we can finish all this stuff. Hopefully next class we can talk about stochastic topic on stochastic modeling for epidemic. The last topic will be uniform persistence. So far, so good? Oh,
I need to.
uniform persistence. 老师应该很熟，对不对？ Uniform persistence. Topic. Uniform persistence. And for this class, we use a very unusual notion up, okay, for uniform persistence. So we don't have to write it again. Yeah. So uniform persistence is a pretty important concept. This is a concept. What it's trying to do? It capture what? What's the big picture? The persistence, right? Something persists. So the long time survival of your population. Long time survival. So you persist.
Uniform.
A uniform, that's another thing. I'm talking about basically. Uniform is saying what? Meaning everyone doing something in the same ruler, same sort of ruler. Okay, uniformly. That's more. So this is really trying to help us to understand the long time survival of the population, whatever the population you care about. And for disease case, of course, whether the infection will die out, will persist, right? Will stand still. Will that be periodic, like the COVID-19 and model you show us yesterday in the workshop? That's like almost, right? You see things come back and forth, persist. All right, so and mathematically, what uniform persistence means? Now, a system now we see this is uniformly if persistent with respect to some set. It's kind of, for disease case, it's some sort of way you're trying to capture extinction. If a uniform persists, you have to uniformly away from the extinction state. Some set, let's call partial Z naught. If partial X, capital X naught. So if there exists eta, this is the uniform ruler, and the such that the limit in as time goes to infinity, the distance between your solution at time t, your solution at current time, away from the set is greater equal to eta, which is true uniformly for all the x0. So you uniformly, roughly speaking, so for disease case, for the populations, the ecology case, some sort of the set. And if you uniform persist, you want to away from that. How far? This eta. But where the uniform is, independent of which point you start with, uniformly at least we are 8 distance away from that set partial capital X0. Does that make sense? So intuitively, what this is saying? it's not quite always the interior, but let me put this one. So roughly speaking, what does this mean? This means there exists a common ruler. How far you are away from the set object your interest. So every solution starting in the, I call the interior, because I want to give you some intuition. Doesn't have to be. This interior basically is the complement of this. So for instance, think about many examples in our biological problem is in the first dimension, the first quadrant, everything has to be non-negative. And then the extinction state, you're trying to avoid the boundary. So that's partial x0. And the interior means the interior of the first quadrant. Is a complement, the whole thing, take out the boundary. What's left? The interior. But basically, fundamentally, that's really the complement. But interior, I want to give you that intuition of whatever the biological domain, biological region. You start any solution in the interior. Now you eventually what? As time goes to infinity, eventually you stay at least 8 units away from the boundary. Again, this is not the true boundary. In general, I shouldn't say boundary. This one. You got the idea. What I'm saying is, when I start inside, because uniform persist is saying I'm not dying. Start inside, I'm not dying. I'm going to maintain at least some uniform distance away from the dying room. That's basically the idea. So that's the mathematical terminology. But I hope you guys not confuse the interior is what. Intuitively, I'm trying to explain this. That's basically the complement of the set you care about. Doesn't have to be interior, doesn't have to be boundary. Kind of make sense? When you start anywhere away from the dying room, let's put it this way, and uniform persistence is saying, at time go to infinity, this means eventually what happened, right? I'm going to at least a certain distance away from the dying room. That's what this is. The uniform is coming from, for one point you pick, you have to find a eta, and another point you have another eta, but this eta is a constant. It's independent which point you pick. So that's what uniform means. So far, so good? Yeah.
About the initial value x, belongs to the boundary.
Interior, no, sorry, not the boundary, the complement. The complement, what our domain is, we get domain B, right? The complement, thank you. You got the intuition, but that's absolutely right. What I'm saying is, if I'm not in the dying zone, and that's why I call the interior something, the complement. And when I start, eventually, I wouldn't say beginning, eventually I will maintain at least a certain distance away. I'm away from this room, so you'll persist. Yeah, thank you. And so the general result for uniform persistence, you have to identify this. No one called that, but I call that. That's how I understand. Some sort of extinction room, okay? You have to identify that first. Then you have to prove the system has a global, the domain you care about has a global attractor. Then on that boundary, the extinction set, this one right here, and I'll call the boundary attractor, is repulsive. called a weak repeller. Then the other thing you have to check, this comes from Morse theory, a cyclic condition. A cyclic condition is saying an attractor, they are isolated. It's no cycle, that kind of thing, connect things. So they're isolated. So that's the essential idea. There are a lot of details. Some of you guys probably are reading or working on this, right now. Is that right? Yeah. So now, here there are some reference your student you may want to start with. And this uniform persistence story comes from Huff, Ford, and so this is 1918 work. The paper is called Uniform Persistent Repeller for Maps. Uniform persistence and repellers for maps. This is the paper published on preceding AMS. And you can find that. Oh, let me put the number. I have it here. And then 1 year later, the same journal, same author, they generalize this bit. Why we mentioned this reference. This is the source of this idea. A lot of time might be easier to read the, yeah. Anyway, so this is source of the uniform persistence idea. Okay. Then 1 year later, same author, they publish another paper. They generalize this idea to continuous time semi-flow. So it's called uniform persistent repeller for continuous uniform persistence and repellers for semi-flow in ordered but not space. Ordered but not space. So same journal, proceeding of AMS. You guys, if you're interested, you can check those out. And you will see initially where those ideas coming from, how it look like. And for the more comprehensive understanding for this topic, I think we already put that reference last time. One is the House-Smith monotone dynamical system. And the other one is Xueying Zhao. And it's not an easy reading book, I have to say. If you are an advanced researcher, that might be handy, but I'm not sure. I shouldn't say that. Anyway, it's a pretty advanced book. So Xueying Zhao's book, we put that reference last time. You guys got the idea, right? All right. So now let's back to, I want to show you this. So if we talk about that, that could be the entire course, just uniform persistence. Yeah. So now we want to revisit our third model. This is what? This is the SR model with simple percent death. Now, because decouple and conservation reduce the model from SIR to 2D SI. So here's how the model look like. Is see this before. So what we want to do, we want to show the following. We want to show this called M3 prime. This is a reduced third model, reduced version short third model. We want to show the SIR model M3 prime is this not up uniformly persist if R0 is bigger than 1. Okay? This is what we want to do. But before we do that, we have to introduce some notations and terminology, okay? Let's do this. So consider a general system. So dx dt is equal to f of x. Okay, now let's say f is defined in this domain and be the subset in Rn. Okay, so now we say a compact, here's the sentence, a compact invariant set, let's say M. Here is containing whatever the system, where the system defined, okay, has been in the domain. And other complement. M is a compact invariant set. The stable set of M is defined as follows. I should say M is be a compact invariant set. Okay, you got what I'm saying. M has to be a compact invariant set. Now, for this kind of set, I can define the stable set. What's that? Is all the points in the complement such that the distance between the solution trajectory start at x0 and M is diminishing as time goes to infinity. So what's this? First of all, why we're take out M? Because start anywhere with M, of course the distance goes to 0. Sorry. Why? Of course, because M is positive invariant. I'm saying you start anywhere in M, this is automatically true. You're not going to get out. It's not goes to 0, it's 0 all the time. So it's trivial. We take those out. Now we consider something, many cases when you see paper on notation, they call M little lambda. Anyhow, so the complement. You guys know why we take out M? Because M automatically true. We're collecting all the points outside M. Then eventually what this is saying, I'm approaching you. Asymptotically, I'm getting closer to you when time goes to infinity. So we collect all those sets. This is called the stable set. You collect all the information that eventually getting or end up at M. So that's called stable set. Now, a global attractor of the system system. What should I carry? I ran out of notation already. Double star. Full star of the system is what? Is the minimal compact invariant attracting set. Attracting what? Attracting set. That attract all bounding subset. Indeed. So this is saying D is your working domain. I take any bounding subset here. And Now, you look into attracting status, and which attract this means as time goes to infinity, where you're ending up with. Now, this set must be compact, indeed non-empty, invariant, and also has to be what? Has to be minimal. Because what? If you have a positive, say, suppose your working domain is already compact, positive invariant. So you are already compact, invariant, attracting set for everything. Because everything cannot get out, right? That's too big. So we're looking at the smallest one. This is true. You attract all the bounded subset in the domain.
About the compact.
Yeah.
Why we need the compact?
So if with compact, you have a lot of things nicer. Structure-wise, compact means what? So topological, any open cover has finite subcover. But the point is, in Euclidean space, compact means something super simple. It's what? Closed and bounded. No, in many cases, we handle that simply because Euclidean space. That's closed and bounded. But in general, that's not true. Infinite dimensional space, that's not true. That's not sufficient. Closed and bounded. In most of the cases we handle, okay? That's closed and bounded. If this is finite dimensional ODE. All right. So here's the theorem we want to use. Uniform persistence. Uniform persistence theorem. We simplify a lot of things. And no, not a lot of things, a global attractor thing. Suppose D be positive invariant. And we assume D has a global attractor. If you're doing general result, you have to prove this first. You show the system is point dissipative, meaning a lot of property, then you can get to global attractor. But now in our case, it will be easy. I'll show you in a second, has a global attractor. So then the system double star, the general system double star, is uniformly persist if and only if the following is true. First of all, the largest compact set a compact invariant set, largest compact invariant set. In whatever the working domain is what? Is isolated. Is this set has to be isolated in attractor A. And second thing, and the stable set of M must be contained in the boundary of D. If this is true, then we'll know from the theorem, of course, that's a lot of work to prove the theorem, the system is uniform persist. So now let's go back to revisit M3 prime, that simple model to see how we're going to do this. In the case where so this will be, let's see. The working domain D is Si S plus I bigger or equal to 0, less or equal to 1. That triangle, that's a working domain. Of course, this is what we already know, this is positive invariant. We also know this is closed and bounded compact. And now the set, our extinction rho will be the boundary of this domain. Okay, so now in this specific example, what uniform persistent means depends on the extinction domain or extinction set you pick. Then that have different meaning. Remember, by definition is there exists eta bigger than 0 such that the distance between我需要一个 limit such that this original definition limit in the smallest accumulation point limit as time goes to infinity, as the distance is at least eta for any x0 in the complement. In our case, what's this? This is the interior of the, right? The triangle, the interior. And now what's this? In our case, this means there exists eta bigger than 0 such that you have 3 boundaries, right? 3 boundaries such that the limit of s as t goes to infinity is greater or equal to eta, then the limit of I as t goes to infinity is greater or equal to eta, and the limit 1 minus also greater or equal. This boundary, and that boundary. So that's uniform. It depends on how you pick your extinction zone. So we are uniform away from all those boundaries. That's what this is saying. What I'm doing is, this is general definition, but that's the meaning in our situation. Because this is solution now, we only have 2 components, right? 3 boundaries. All right. So here's what we want to do. And we want to show when R0 bigger than 1, the system is uniformly persist. And one thing is pretty straightforward, because the region is what? We know more. Not only bounded, this region close and bounded is compact and positively invariant. So what do we know? A global attractor must be located inside. Because what? The whole thing already is non-empty compact positive invariant set that can attract any bounded subset, because that's too big. We're looking for the smallest. So, and we know there exists a global attractor. That's the smallest one that can do the job. That's already too big. The big one already can do the job, but that's just too big. So we know there is this global attractor. So now, we call UPT. To apply the theorem, all we need to do is to check what's the largest compact set, right? So let's do this. Largest compact set in the boundary. What's the largest compact set? In the boundary. The boundary is this one is what? The disease-free equilibrium, we call it E0, is 0, 0. Along the boundary, nowhere is a stacking or fixed point except this one, right? Okay. So now, of course, which is isolated. It's just one point. And second thing. The second thing is what? The second thing we want to check the stable set of M actually is cannot be get away from the boundary. 哎，刚才 stable set， 这个 stable set 是所有的那些点 eventually can attract to M。Sorry， 这个 M 是啥 ？M 是这个 single point， 是所有的那些点 can eventually attracting to this point。哦 ，OK，all right。现在的问题是什么？这一点是什么？是一个 when R0 bigger than 1。When R0 bigger than 1, what do we know? We know this singleton disease-free equilibrium is unstable. What this means? This means it's a repeller. It's a repeller. If R0 is bigger than 1. Let's all equal to 1. 这个点是 even not only stable 是 global asymptotic stable. 所以 when R0 bigger than 1, we know E0 is repelling towards the inside of our domain, right? So it's a repeller. Now where you have to, because you're repelling from the inside, so the only thing you can leave is whatever the things left. That's the boundary. That's it. So then by the theorem we know this one, the system M3 prime is uniform persist when R0 is bigger than 1. 我们现在偷懒了，你知道吗？我们没有证，一般我们去做，比如说做 partial differential equation 的时候，我先要证明我的 system point dissipative， 就是说要满足性质，最后我要证明它存在一个 point dissipative， 就是说你不能有太复杂的 system， 它会有一个 global attractor。我们现在这个简单，为什么呢？因为我们的 working domain 就是一个positive invariant region which is closed and bounded。这已经太大了，那它再往里吸，它不会是空的，为什么呢？因为我们刚才证了 asymptotic property of omega limit set， 它 must be non-empty， omega limit set 一定在里头。而事实上，在我们这个 case 特别简单，那 global attractor 就是 union of all the omega limit set，a closure of the union of all the omega limit set. But we should not, in general, what I'm saying is, we do not need to identify what's A. We just want to show there exists such a attractor that can attract all the bounded subset in the domain. 我说的意思，之前要去证这个，然后剩下的话，像我们这个一般来证这两个就够了。这个就是那个 repelling on the repelling property。然后这个就是说它是 isolated。
About this point,
对
I not realize why it implies it's a repair.
因为它如果是 unstable 的，它的那个 direction， 它的 eigenvalue 的 direction 是什么？它是 point 是什么？
Outside the boundary.
对呀，它是 push out， 所以它不会往里走嘛。那不会往里走，它最后剩在哪儿了 ？The boundary。所以它会 retain the boundary， 它进不去，它一进去就被 push out。
如果其他的
对，
就是 eigenvalue 都是
0不行，那个不行。eigenvalue 是0，那个需要 further study， 那个是一个 tricky case， 对，那是一个对，那个不行。我们现在这个知道的那个 local stability， 我们上次已经做了，就是
我了解。
对，
如果 apply 到这个 model，
对，
我是说这个 general 的
对，不行，那不行。那时候你可能要构造 Lyapunov function to prove that。对，这是另外一个办法，就是construct a Lyapunov function 去用这个 Lyapunov function 去证这个 repelling property。然后还有一种办法就是 contradiction， 这个得用 comparison principle。对
apply 的层面
对
我理解。
对
back to
对
的 theorem 的写法，这好像没有排除的那一个刚刚讲其他的 eigenvalue 如果都等于零。
你都等于零的时候，它得就是说你的 linear term 就是 degenerate， 你还要看 higher order term 才知道它的 dynamic 是什么样的。如果你能知道它还是 repelling 的 repel from inside 的，所以你只能 go to the boundary， 它就是这个意思。那个同学可以休息一下了，因为已经11点了，我们休息15分钟好吗？对，郑老师你讲。Let's take a 15 minutes break. Sorry. Shall we take a 15 minutes break? Okay, all right. 我忘了他。
对，不好意思，线上听不到声音。
谢谢，这样可以吧？
谢谢老师，谢谢老师。
不好意思，我给忘了。现在是 unbound real matrix。就是相当于是说，想我们 linear system， 然后看那个系统是合作的，要求什么，就是这个。
octagonal 废符。
哎，这就合作了，这叫 modular matrix。哎，就是 off diagonal entry 都要 non-negative， 然后它还有几个 notation。网站里面直接。就会写几个码 A， 是它那个 collection all the eigenvalues。这个就叫 spectral。spectral radius。有的时候你看到 paper 也会写是 RA 或者是 RA， 都是 spectral radius。它怎么定义的呢？我们 finite dimensional 很好读，是
最长。
对，最大的。这样写也行，但不一定是。要看 magnitude， 就是说相当于是我们之前讲过，找一个圆盘，最小的 size 能 cover 所有的 spectrum， 它那个 size， 那个 radius 是那个叫什么？那个 disk 的 radius，smallest disk that can cover all the spectrum， 对 ，the spectral radius。但是这 finite dimensional 太简单了，就是什么？取那个绝对值最大的那个，对。然后还有是 spectral abacus， 是好几个名字，这个也叫 stability modulus。modulus 我是不是没写对呀？是什么？是叫 S of A 是什么？是最大的，因为我们知道 stability affected by 什么 real part eigenvalue，我们取它的 dominant real part。如果写成sigma，这个不应该写，对 ，anyway 就是这样。super，因为谱不一定是 discrete。第一个问题是说，还有一个 definition， 然后我们说一个 matrix A 是 stable 的，什么意思呢？这个从哪儿来？我们一会儿再说。我们先看第一个结果，叫 Parent-Fubini theorem。Fubini。这个大家都知道，这是 component wise， 或者是对一个 matrix 是A 大于是 component wise。然后说一个 non-active matrix， 然后我们会有如下的结论。第一个就是它的 spectral radius 事实上是它的一个什么？事实上是它的 dominant eigenvalue， 所以它最大的 eigenvalue 事实上是 spectral 那个 radius 还得是非负的。最大的 eigenvalue 是 real 的，是非负的，因为那 eigenvalue 它不一定是 real 的。存在一个 v 大于 w such that AVW 就是 spectral radius of a non-active matrix is going to be its dominant eigenvalue。这个最大的 eigenvalue 它是非负的，当然它有可能是零，因为取零 matrix 之类的，对吧？对，是非负的，而且它是 real 的。但这事实上也告诉我们一件事情，这告诉我们什么？我一会儿再说。我先把定理写完了。第二个是说，如果the non-active matrix is irreducible， 我们上次定义了什么是 irreducible， 对吧？Then 这个 eigenvalue 它是 simple 是什么 ？algebra multiplicity 是 1， 它没有 repeated 的那种，是 simple eigenvalue。再说 simple 是什么意思？是 simple eigenvalue。换句话说，它是 algebra multiplicity 是 1。OK， 然后呢，这个时候更强了 if A is irreducible， 我要存在一个 positive vector， 这是 component wise such that 这就是 Parent-Fubini theorem。然后这里第一个 comment 就是从这里我们看这个是什么呢 ？In this case， 如果你有个 non-active matrix，what's your largest eigenvalue？ 你已经知道了，它不是 complex， 它是 real 的，它是谁呀？是一样的，对吧？哎，那我再看，现在我要讲 Parent-Fubini 定理，它的那个methods of matrix version。为什么我感兴趣？因为我感兴趣 cooperative system 嘛。matrices， 这个 matrix 现在我还叫 A 吗？我换个名吧。还有那啥呢？我现在也叫成这个。好。这个时候第一个结论是什么？第一个结论说，我知道它其中的一个 eigenvalue， 或者是它属于 这个是什么呢？是 spectral abacus， 它是其中的一个 eigenvalue。第二个，当然我也能找到一个 non-negative vector such that f 等 s。Let me know if I copy it. OK， 经常大家都特别 pay attention，我非常的 appreciate。有的时候我说的和写的是完全不一样，好 confusing。对，第二个是什么呢？第二个是说，如果这个 m 是 irreducible， 会怎么样呢？这个 eigenvalue 是 simple 的，当然你还可以写简单一点吧，是在一个这么说好了。Suppose we know this, how are we going to see this? 这个是一个大定理，对吧？开尔夫宾尼定理，我们已经知道它结果是这样子。但是如果我们知道这个如果对现在我看的这可不是一个 non-negative matrix， 这只是 off diagonal entries are non-negative. I have no control about diagonal, so 这个怎么看呢？就差一点儿，对吧？那一点儿，我们想想有没有什么办法？
minus epsilon i。
哎，来，我们来试试看哦。idea 就对了，就我们来看 P idea 就是这个。这个 M 是 not non-negative 的，对吧？但是差不多。All you need to worry about 就是 diagonal entry could be negative or something like that， 对吧？所以我现在就取得很粗啊，我就说。哦 ，sorry， 我的觉得，which 是所有的 I 是 M 这个是嘛，就这样，对吧？不取它，那就好办了。我现在看一个新的 matrix 叫 A 是 M 加上什么？啊，就阿尔法就行了，阿尔法 I。那这个新的这个 matrix 有什么性质？刚才我说了，那个 modular matrix 和 non-negative matrix 就差 diagonal entry， 对吧？那现在是如果我加了这个，是说我不知道它正负 diagonal， 对吧？正了当然更好了。如果它要是负的话，我也不怕，我把它揪出来。那这个 matrix 有新的这个 matrix 什么特点？这是一个 shifted version 它，对吧？这个是什么？对，那就好了，可以用 parent 辅宾尼定理到这个上面，对不对？那你看这里的，我现在这样写，大家应该懂，对吧？这个是什么？这是它的每一个 eigenvalue 和它有这样的关系，对不对？然后它其实就是它的 spectral 的一个 shift plus alpha， 对不对？那特别的，我要是取 maximal real part， 我现在取 real part， 我取 maximum， 再取 real part。这个是不是还对？对吧？这个还对，对不对？那这个是什么呢？对，这是它的那个 stability modulus， 对吧？那这个就是它。可是 by parent 辅宾尼定理，我们知道什么？它的 spectral radius 和它的那个 stability modulus 或者它的 abacus 是一样的。那换句话说，我就知道了，我还能找到那个对应的 eigenvector， 因为就从 parent 辅宾尼定理嘛。这个它应该是就等于它减去阿尔法，它应该是它的一个 eigenvector， 对吧 ？That's it， 就能看出所有的这些结果。 那现在为什么我们感兴趣这种？因为我们如果做 monotone dynamic，为什么做 monotone 呢？因为我们需要能比较，高维的时候没法比，它建立了一种。And so monotone dynamic system give us a way we can kind of preserve certain order or like in certain way. You know how to compare. And so the dynamic will not be that complicated. Now and also a key concept in monotone dynamics is something called cooperative. Roughly speaking, suppose you have two species. So the increasement, like I say, if you increase one of the species, will not decrease the other component. So they are cooperative. But this is not going to be a case for the say the predator-prey logical water model because they are competitive. So that's the general idea. Anyhow, 为什么我们再说几个 property of metal matrix？ 我把这个地方 clean 了，可以吗？这个清楚了吧？对吧？这个就是它的，它的一个对。我们再讲几个 several 嘛 ，several useful property。Interesting。一个 system 是 n 维的，就分好了。Square matrix. Then the following are equivalent. The following are equivalent. 所以说，如果这个 metal matrix 是 stable， 为什么我们 carry 它 stable？ 一会儿我们来看啊，它是 stable 的。另外一个刻画是说，它是 non-singular invertible 的。那它的这个是大于等于0。第三个刻画是说 ，for any b positive vector, there exists x strictly bigger than 0, such that we can solve the system. 我们来看看这个就是想干些什么。这个都是 equivalent 的刻画一个 stable 的 metal matrix。对。我先说一下 motivation， 我们再来看这是怎么回事。我们为啥要讲 metal matrix？ 刚才说跟 monotone dynamic system 有关。最简单的 system 肯定是 linear， 对吧？所以如果 A 是一个然后我们来看这个 system， 我们大家知道什么？知道它的 solution 长什么样，对吧？它 solution 长什么样？它的 fundamental solution 是啥
？Solution A 题。
对，这个对吧？是这个对不对？那现在就来了，如果它是 metal matrix， 我们一会儿看它对应的这个 linear system 就长得这样，对不对？这个 linear system 它会是什么 ？monotone， 就是说，如果我 start with x0 是大于等于0的，我们会知道什么呢？ xt， 也就是它会大于等于零 all the time。对，这是 monotonic。那现在我们来看这个，这个就是说，因为我们做一个非象限系统，然后对它做linearization local analysis 的时候，一定会碰到这种东西，对吧？然后它的 structure 就相当于我们之前做的那个 linear system， 你看的 Jacobi， 然后它 Jacobi evaluate 在那个 fixed point， 它就是一个这样的，对，这样的一个 matrix， 它实际上是一个合作的系统，它是 monotonic。来看这个 A 是 stable by definition 是啥？我们 quick 看看 T I D 就好了。A 是 stable 的是什么 by definition？ 我们这样写A 是 stable 是什么意思 ？A 是 stable 是说它的 stability modulus 是负的，对吧？对，是这个，这是 definition 对吧 ？A 是 stable， 这是我们知道的。我们想问为什么 A 是 invertible 的？这咋看 ？Question clear, right? I have a Matrix matrix。现在你事实上不需要 Matrix， 你只需要知道 spectral 不是 spectral radius， 只是 stability modulus 或者 abacus 是负的，是 negative。为什么？为什么？为什么？为什么？这个是 non-singular 或者 invertible。singular 一定会怎么样？假如说它 singular， 它会怎么样？别着急。
有 eigenvalue，
对 ，zero 一定是个 eigenvalue。那 zero 是 eigenvalue SA 会怎么样？哎 ，that's it， 有清楚吗？我说，如果它是 singular 的 ，zero 一定是它的一个 eigenvalue。如果 zero 是 eigenvalue， 你取它的这个 real part 最大的时候，这个最大的一定是大于等于零的嘛，对吧？所以就不可能嘛，它一定是 invertible。那我知道这 invertible， 那这个东西又怎么看？这个东西怎么看？对，想想，没错，他说的都很对，非常好。你先想简单的，如果 A 是数的时候 ，A 是数的时候，我来看这个 A 是个数啊 ，one by one， 比较急。这个等于什么？如果它是个数，我把它换成 A 好了，这样看，好吧？这是什么？我们都会嘛 ，fundamental zero calculus 这是啥？我们一般是这样写，对吧？我现在 matrix case 我没有这个东西，我是它，对吧？对不对？对，就是。那现在我现在想来看它，这个是 one by one matrix， 这是 n by n matrix。这个时候我们 guess 它是啥？我不知道。minus A inverse。然后那为什么呢？如果你给定这个 matrix， 你都不需要它什么，这个地方它都是非负的，对吧？它这个积分一定是，我说如果这个 relationship 对的话，如果我还不知道，那它这个大于等于零就自动的了，对吧？没错。好，我们现在就要来争这个。看这个咋看？可以，还有可以做 Taylor expansion。你看这个东西的 antiderivative 是什么？这个东西的 antiderivative 是什么？是 A inverse 是 E 的 AT 嘛？对。那我现在来看这个，刚想凑的就是它嘛，对不对？这个我们知不知道？这个是什么？Do we agree？对吧？我都没讲，我们知道怎么定 exponential matrix 吧？就是那个 Taylor series 那个展示用那个方法去定义的，还是个 n by n matrix。好 ，so we all agree with this, right？然后这个是等于什么？是 A 是 constant 是 independent t 的 ，we can pull it up。 我们要的是它，对吧？是不是？那你来看这是的东西，我都知道 antiderivative 了，我可以做 fundamental theorem calculus 了，是吧？这是什么？这是什么？这是它 evaluate t 等于0和 infinity， 0的时候是什么？
identity
对，就是一维是一，高维的是 identity， 对吧？那 infinity 又是什么？这是什么？是 matrix 没错，别忘了我们有个条件还没用呢，这儿呢，
stable
这是啥？因为它的 stability modulus 是负的，所以 exponential at 它要当去 t 去分，它是 exponential decay 的，它是 matrix 啊，它可不是一个，它是个 functional matrix， 它是 exponential decay to 0的，对吧？所以这个负这边是什么？就是零这是不是零？这是零 matrix， 这是负的 identity， 对吧？所以我们就看出来了，对不对？所以你两边同时除以 a inverse， 是不是就得到了负的 a inverse？等于它，对，所以它是一个什么？我不知道你们记不记得，在 disease case 我们会把那个整个 linearization 做一个 decomposition， 一部分叫 F， 一部分叫 V， 对不对？你现在想，如果这个 matrix A 就是 V 的话，是不是我们常常见这个性质？Anyway, so from 1 to 2, from 2 to 3 is almost trivial. For any b, 这个可解是因为 a invertible， 对吧？你肯定可解，对不对？它大于0是因为什么？是因为负 a 的 inverse 是大于等于0，因为这个时候的解是什么？解就是负 a inverse b 嘛，对吧？当然大于0。然后从这儿到这儿的话，你就取一个就做出来了。从这儿到这儿也是trivial，从这儿回来。大家可以去，我就 leave it to you as exercise. What I want to say is， 现在如果我有个 master matrix， 它是 stable related to 我们原来那个 system， 它是 dissipative 的。这是它的 equivalent characterization. Sometimes one is way more handy than the other one. 然后我们来讲最后一个，是最后几个，来看还有什么。最后这个为什么飞了这么大一圈又回来了？因为从这一步再回来比较好用。从这 5到1你要用的那个 parent 伏比例定理，因为 parent 伏比例定理刚才我擦了，它会 related 会找到一个 eigen non-negative eigenvector， 使得什么？使得它是它的一个 eigenvalue 嘛。要用到那点，然后才可以回到这个。OK, all right。现在我们做这个半天，就是因为 Maxwell matrix 这个 concept， 我要说 count 一个 matrix， 它是 related to monotone dynamic system。Again， 我们现在知道 monotone 是什么意思？我们已经知道了这个，我们上次讨论过的，它是这个我们讲不是 R 到 Rn 是 Euclidean space， 它是 monotone。它这时候那个 positive cone 就是 first quadrant。In general 可不一定是对，取决于你的那个 balance space、order balance space 是啥样的。然后它是 monotone 就是什么意思呢？imply 这就是 monotonic 的意思，你 maintain 一种秩序，一直可以这样做下去。 这是一个 partial order。All right。那 linear system 我们刚才已经看到了，这是对的，对吧 ？linear system 我们刚才已经看到了，它是对的。现在我们再讲一个结果，这个可以。2到2的 system， 它属于具体范式中，所以你能看这个位。然后 we assume is positive invariant. 这是 positive type。这是我们都人大的对象调查了。哦，这 triple star 吧。System是 strongly 通畅。这个叫强单调，是吧？这玩意儿是 strictly sublinear， 这个 notation 我们都讲了。X 是 strictly sublinear。And solution to the system is bounded. Or 0. Then we have the following. 为什么我们喜欢 monotone 或者是 strongly monotone dynamic system? We have the following. 比较A 吧。Yes. F0 is 0. So origin is a fixed point. So this case have two possibilities. All solution will converge to origin. Or there exists a positive steady state. What should I call it? Positive steady state, and which is globally asymptotic stable in this region. If F evaluate origin is positive, there exists an equilibrium solution. 这是个 fixed point. Positive equilibrium solution. That is globally asymptotic stable in whole Earth. This rule out the case origin is the fixed point. 我们现在看看这个定理说点什么玩意，就说 像我们之前讲的那个好多的那个，因为是 2D 的，有更多的工具可以用，就是说你可以直接用这个结果来看它的 dynamic。这是基本 setup， 这个是说这是我们的 posicon 是，这是那个序建立的地方。说这个 region 也是 biological physical region 是 positively invariant。You initially start there, when you are moving forward, you stay there. 然后 this one is saying it's strongly monotone. Strongly monotone 大家还记得是什么意思吗？在我们这个地方特别简单，就是每个 component 如果 initially 你比它大的话，然后你 stay 它比它大，但是如果它俩不完全相等的话，这个是 strongly unequal relationship 是 strongly true 的。我说的是 x if we have this but x0 is not equal to y0。And 这个不但这个对，而且是什么？这个是 strongly agreed， 对，这是 strongly monotone， 我们上次讲过。然后下一个是 sublinear 是 component wise， 我们看什么？忘记了 component wise 看这个。For any lambda to 0, 1， 对。然后最后一个是 system， 它的 solution 要 bounded 的，不能 unbounded。然后结论是告诉我们是什么？如果 zero 是个 equilibrium solution， 所以这时候所有的 solution 都会 converge to zero， 或者是你存在一个 positive 的 equilibrium， 然后它还是global asymptotic stable。如果 origin 不是 equilibrium， 这个时候你会找到一个正的一个平衡点 equilibrium solution， 它是在我们这个空间是全局全极渐进。globally asymptotic stable， 全局渐进稳定吧？对，那看这是什么意思呢？这个是说，这个是我们 working region 对吧？进去不会出来。这个首先这个是说明我这个 problem 应该是 well posed 的。这个是说给了我们一个办法，我们可以去比。那一旦可以去比，你就不会出现什么？你就不会出现 crossing， 你一直在这种 order 下，我们一直走，不会是说，假如说原来是这样子的，自走自走变成这样子，它不会有 crossing。好，这个是什么？这个是说，我的理解是说，如果你 close to the boundary， 它会 push you away，avoid you go the other side，push you away。为什么呢？你看，当那个 x 很小的时候，这个 lambda 是一个 scaling factor。当你 close to the boundary 的时候，它至少有一个 component 是零，它比原来的那个值 evaluate 在刚才有一个至少有一个 component 是零，它还来得高，所以它就 push you away from the boundary， repel you。对，怕的是什么？这怕的就是说，你一旦达到这个 boundary 了。那这个 system 有可能就会 end up with 什么呢？这叫 boundary equilibrium。比如说那个叫什么？是不是叫 predator-prey model？ 对 ，Lotka-Volterra， 它有竞争的，它有的时候取决于它的那个parameter 这个 model 的 situation， 它有时候会 end up one species survive, the other one not。它现在就是这个条件，就是因为这个条件，你就 guarantee 了你不会有这样的情形，你会 avoid 它 end up 在这个 boundary， 因为一到你 close， 它就 push you up。你看这个不是大于等于，这是 strictly bigger than。然后 the last one 说就是说的解不会 crazy， 是 bounded。那你看，它现在告诉我们这 dynamic is super simple。我记得我曾经 promise 你说我们会。看那个，我想想，有两个都可以。M3 是说 SAR model with simple birth and death， 还有一个 M5 就说第5个 model 是什么？是Ross McDonald model for malaria。那两个 model 我们都可以用这个理论，就直接验证这4个条件，就可以看它的那个 dynamic。我们当然可以用其他的方法去做，因为 model 很简单。我现在就是这叫什么？杀猪用牛刀啊，这是个很大的一个刀。对，我们可以去看它的那个 那个结果。对，今天就到这里。我们今天结束的有点早，我们从下一次开始，希望我们可以就是我们可能要 switch the angle， 我们要去讲 stochastic modeling。对，从下一次课开始。So that's all for today, and thank you very much for your attention. Any questions, comments for the folks online?
你看 P 不一定是一个约人，比他里头 OK。
不可能有 periodic， 我们不可能有 periodic。现在这个是说为什么这全是叫平衡点是吧？对，就是非常 simple and clear 的这个 dynamic。
不一定要 isolated， 就是可能有所有的平衡态。
不能啊，刚刚说了就这两种。
可是它就是只有一个点，不一定。我的意思就是，
它的平衡点可能有不止一个，但是它的 dynamic 是 super simple。他刚才说了，这个可叫 global。那事实上，这个情况下就是两个平衡点嘛，或者是 zero， 就是 R0。我们现在做的具体例子 ，R0 小于等于1的时候，那个 origin 就是 disease free 那一点，它是那个 GAS 就是 converted to 它。或者它有个存在一个正的平衡，这是 R0 大于1的时候，所有的点都吸引到那个正的平衡点。刚才我说了，它这个条件就是 guarantee 你不会有 boundary equilibrium。对，这个是说0点根本就不是一个平衡点。对，在这种情况下 ，dynamic 更清楚，就是全部都是 dissipative 去那个正的平衡点，在 interior 的，就这个意思。我们现在套的不是 banana space， 我现在放的所有的这个我现在把这定理放在哪儿了？放在我们的 first quadrant 了，就是我们至少我们的如果是个 biological realistic problem， 我们一定 work with first quadrant。
应该空是第一象限还是任意空？
我现在这个空就是第一象限，在我现在举的这个例子里，对，对，这对是，对，是的。那个 order 建立起来的，你刚刚说那个 partial order 就是什么怎么比啊 monotone strong monotone anywhere， 它那个是建立在一个 positive 空的。它如果是 strong monotone， 它要 lie in the interior of 那个 positive 空，那是 strong 的。如果你只有 monotonic 的话，是说你维持那种秩序嘛，对不对？但是如果你是 strong 的话，它的 difference。就是它有一个 strong 的那个 inequality， 他说不只是我和你不一样，我俩完全不一样，不能有一个 component 是一样的。说就是在这个 situation 是那个意思。正常的是 general topology， 我不应该这样说。我说的是它要 lies in the interior of your positive cone， it's way stronger， 就这个意思。那是 strong monotone 的意思。对 ，That's all for today. Thank you. 希望大家有个 Happy Black Friday。这里应该没有 Black Friday 的什么，对吧？我们像在美国是取决学校，Black Friday 会放2到3天，我们学校放1周，这是我们的 Fall Break。对，好 ，Happy Friday，I'll see you next week。